All right, let's get into it. Today, we're diving deep into one of the biggest, most exciting challenges in tech today. How do you actually build a humanoid robot? And we're not talking about theory here. We're going to follow the real, step-by-step journey of a builder.
I mean, think about it. Building a person-shaped robot from scratch. It sounds like something straight out of a movie, but it's really happening. It is, an incredibly complex task. So where would you even begin? Turns out there's a surprisingly clear roadmap that can take you from just an idea to a walking, thinking machine.
So we're going to follow a proven 13-week path that developers are actually using to take on this exact challenge. It's all about breaking down a huge, almost impossible goal into smaller, manageable, and absolutely critical steps. This is basically the blueprint for building a humanoid.
Okay, so first things first. Where do you start? Before a robot can walk, or think, or do anything really, it needs a nervous system, a way for all of its different parts to talk to each other. This is the absolute foundation. And, maybe surprisingly, it doesn't start with hardware. It starts with software.
And that digital nervous system? It's called ROS2, which stands for Robot Operating System. The best way to think about it is like the universal language for all robots. It's this amazing open-source software that makes sure the motors and the sensors and the computer brain aren't just a bunch of separate parts, but a single, unified system that can communicate perfectly. Getting the hang of ROS2 is kind of like learning the grammar of a new language. You have nodes, which are like the individual workers, one for the arm, one for the camera. Then you have topics, which are like public announcement channels where those nodes just broadcast what they're doing. Services are more like direct phone calls for specific requests. And launch files, that's the master script that tells everyone to get to work in the right order. If you get this right, you've built the communication backbone for your robot.
So, with that nervous system designed, you might think, great, time to start bolting metal together. But that's the old way of doing things. The next critical step is to create a digital twin, a virtual copy of your robot that acts as both a blueprint and a digital playground.
And this digital world gets built using these incredibly powerful simulation engines, like Gazebo and Unity. And trust me, these are way more than just tools for making video games. They create these hyper-realistic environments where you can build, test, and even break your robot 1,000 times over, all before you spend a single dime on physical parts.
And this is the absolute game changer. See, in the virtual world, failure is just data. A robot falling over is a learning opportunity. You can test 1,000 different ways for it to walk in just one afternoon. But in the real world, one of those falls could mean weeks of repairs and thousands of dollars down the drain. Simulation is what makes moving fast and innovating even possible.
Okay, so we have a virtual body and we've got a working nervous system. Now it's time for the really cool part, giving it a brain. This is that moment where we go from a machine that just follows instructions to a truly intelligent agent.
And the engine for this AI brain is a platform like NVIDIA Isaac Sim. Its whole purpose is to solve one of the biggest problems in robotics, bridging what they call the sim-to-real gap. It gives you all the tools to train an AI in that virtual world so effectively that it can work in the real world with almost no changes. It's a huge deal. So what does this AI brain actually do? Well, it enables 3 key things. First is perception, the ability to actually see and understand the world around it. Second is manipulation, skillfully grabbing and using objects. And third, and this is the really wild one, is reinforcement learning. That's the ability to learn complex tasks just through trial and error, pretty much the same way we do.
Now, we take that powerful AI brain and we apply it to the ultimate hardware challenge, the humanoid form. Seriously, making a machine walk and balance on 2 legs is one of the most notoriously difficult problems in all of engineering.
See, the goal isn't just to build a robot. It's to build one that can operate in our world. And that means mastering bipedal walking, which is a constant, incredibly complex balancing act. It means being able to pick up and use objects with human-like skill. And just as important, it means designing its interactions to be safe and intuitive for all the people it's going to be around.
So after weeks of mastering the software, perfecting the simulation, and training the AI, it all leads to this moment, the capstone project. This is where every single piece of that puzzle finally comes together.
The final hurdle is always integration. I mean, it's one thing to program a walking algorithm by itself, or to get a grasping motion to work in isolation. It's a whole other ballgame to make all of those things work together, seamlessly, in one complete system. This is the final exam, proving you can build not just the parts, but the whole thing.
And what does that final creation look like? It's a fully simulated humanoid robot that can not only move around and interact with its environment, but can also communicate using conversational AI. It's a true physical AI agent.
So when you look back at it, this whole builder's journey is just a really powerful logical progression. You start with that foundation, the ROS2 nervous system. Then you test and you refine everything safely inside a digital twin. Then you give it a spark of intelligence with powerful AI. And finally, you integrate everything to assemble a complete simulated humanoid.
What a journey like this really shows is that building a humanoid robot isn't some kind of black magic anymore. It's a science, and it has a clear roadmap. The tools are out there, the path is laid out, and honestly, the barrier to getting started is lower than it has ever been. So the real question isn't if we'll have humanoid robots in our lives, but what we'll build them to do once they're here.